Værsgo at sidde ned, og sorry for my language. Please sit down. Have a seat. Let's move on to real descriptive statistics, summary statistics. We do that in two small parts. We start out with the list of the things that I will show you, as I promised you. I'm going to teach you how to compute the mean of the data. I hope this comes as no surprise. I think one of my daughters saw this in the second or the third grade of the Danish public school. So I think that should be familiar to most of you. Then we rapidly move on. Median, variance, standard deviation, and percentile. I bet you couldn't define all of them just like this. So it's not hopefully a completely waste of time. So the mean, here it is. What does it say? Maybe not all are familiar with summation signs like this, the mathematical summation sign, but in case you're not, I'm sure if you follow the math course, you will be familiar with this. And if you have followed it, it's not a big deal for you. It's just a way of saying that I sum up all the data that I have and I divide by the number of data points. Right. That's, we're going to do a small example because I'm going to need a little data that to play around with. Heights of young, what should we say, males. So we do a random sample now. Your first random sample of this course. And I throw a 270-sided dice. Let's see, how many males are we in here? Like 150, let's say that. You're 150. So I throw a 150-sided dice, and I get the number pointing at you. You came up. If you want to play, tell me your height. If you don't want to play, just say, fuck, no, don't say that. Say, not me or something. 175. I throw the dice again, a random dice, 150. But it points at you. I throw the dice again, and it's a random dice, and it points at you down here in the front. 70. And I throw the dice once again, randomly, at you. Okay, it's okay. I had a double dice here. Both of you. And I once again, it was you. 82. Okay. Let's stick with this sample. We don't have all day. So we took a random sample of 5 persons. Let's see. Philip, can you, sorry, Jeppe, can you help me with these numbers? Or don't you have time? No? The sum of these numbers would be 75 plus 93 plus 173 plus 174 and the plus, yes? Let me have times 5, that is then, the sum is 897, meaning that if we compute the average, it's then 897 divided by 5, which is, what's this? This is the average of you 5 persons. If I take you as a random sample of the population of young males in Denmark, maybe you're not Danish, all of you, but then at least let me, young males of western part of the world, not even that, maybe as a sample of the whole world, then this is just as it is, 179, but what statistics amounts to is to take this further. We're not going so far today, but then it would be a guess of the real mean height of young males. It would be around 180. It's a pretty good guess, actually, I'm sure. So a 5-size sample can be pretty good, maybe. I'm going to teach you in this course how good or how bad such a sample really is to help us. That's the key part of the course. Now, running back. There are other ways of telling the story about, you could say, the mean, the middle, the most typical data point. There are different summary statistics. Also, even more than I'm showing you here. One we're going to just meet again is the median. The median is you could say, the middle number. It's the number in the middle. How is that defined? Well, you sort the data and you take the number in the middle, right? So if we go for the median, this was sort of the mean. I'm going to share these notes with you afterwards, like that's part of it. I'm going to PDF it and share it online. The median. Then we would order. We have the small guys first. Sorry. We have a guy in the middle, and we have this awkwardly large guy here. Sorry about that also. What is the middle number? 1, 2, 3. This is the middle number, right? When there is an uneven n, there is a middle. So here median would be 175. Now the difference also between, let's take that, one of the difference, there is an obvious difference in how it's defined, the median, the mean. The difference in when it could make good sense to use one versus the other is related to whether we have nicely distributed data or we might have odd outliers, odd sort of individual numbers. If we had an odd, let's say we have another, let's say we had an additional data, so we have n equals 6. We have all the 5 from before, x1 up to x5, and then we have a person which I know very good. Here. I have to be, no, I'm going to lie. I'm lying. Like this. It depends, it's when you get older. This is the random sample. Now, if we take the mean of this one, a mean is more sensitive to extreme observations, right? If you put in one extreme, it's going to change the mean a lot. It doesn't have to change the median a lot, right? Because the median is the middle point, so the median doesn't care about whether the largest guy is a 240 centimeter guy or the smallest guy is a 120 centimeter guy. The median doesn't care. The median is just the middle number. It's not affected by these extreme points, which the mean is. So that was one point to make here. Actually, the other point I wanted to make was if n equals 6, there is no middle point, right? We have 1, 2, x1, x2, x3, and we have x4, x5, x6. Actually, sometimes you use such a notation here to indicate that these are ordered. So I have the 6 observations in an ordered sequence. There is no middle number, so the median would be the average of the third and the fourth observation, right? That was just to exemplify this. Good. That was the median, a more robust measure of where we are. Recently, there was a discussion a few years ago with how to monitor and how to put goals for the response time of emergency driving, ambulance. What's the English word for ambulance? Fantastic. Ambulance. It's so easy to speak English. The ambulance times in the Copenhagen area, should you look at the mean time or should you look at the median time? what they did was to change without telling from mean to median. It's a right-skewed distribution, actually, so it looks better with the median. It's also fair with the median, but they just... it's a long story, I'm not going to dig into it. But it's just to say it can actually matter a little bit how you tell the story. It may... And if people have in their minds, and I'm sure people out there, my parents would not worry too much about if they heard in the media that the median time was these 6 seconds, or the mean time was 7 seconds. Well, this is 6 and this is 7, that's not the same. So I think people would not think about, you in the future will think about that, to help society be enlightened and make good decisions, right? So it can make a difference, actually, also out there, whether you use one or the other. Both can be nice in their respective places. So we use the mean a lot also for matter of convenience, but mathematical and theoretical convenience, actually, we use it a lot. Let's move on to a very, 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 very important summary statistics of this course. Namely, I call it, in a way, just one summary statistics, even though it has two forms. It has the squared form, which is called the variance. It has the square root, which is the unsquared form, which is called the standard deviation. And I mean, it's the same number, right? Understanding same the right way here, right? It's expressing the same thing, just on two different scales, you could say. What is the variance, respectively, the standard deviation, really? It's a key number to measure variability. And variability is at the heart of this course. So we're going to use variances and variances and variances again. Not only this variance, but extended versions of other variances. But the concept of a variance and variability is really at the heart of this course. Okay, what is a variance? A variance takes each individual observation, subtract the mean. So you take how different is each individual person in height compared to the mean height of 179. How far away is the individual person? Then you add this up, the difference, the deviation for each individual. You add them up. No, you don't add them up. You square them and then you add them up. And you mean them. You don't mean them, but you almost mean them, averaging them. It's from a conceptual understanding, from an interpretational point of view, we take the average squared deviation. So for interpretation, it doesn't matter whether it's n or n minus 1. You can take the n minus 1 in a sec. It's just more or less the average. If it's 100, it doesn't matter whether you divide by 100 or 99. It's still the average. We're going to try this, of course. Try this on the data we have here. The mean was... Usually I'm cheating, but I didn't cheat so much. I always cheat, but I usually cheat more than... Anyway. Maybe someone can help me here. I want to put in a table here where I put the x's. Can you help me now? 73, 74, 75, 82, and I remember the last one, 93. The mean was 179.4. Now we subtract the mean from each of those. This is difficult now. Minus 6.4 minus 5.4. I may... Now, please remember to correct me when it's very easy to do. I mean, it's very difficult to add two things here when you have 250 eyes, 500 eyes looking at you. So please help me and don't just enjoy the moment of embarrassment, right? And I know this is nice and it's part of life's entertainment, but please help me, right? When it goes wrong. You may enjoy the moment of embarrassment just a little bit. I mean, that's okay, but not too much. Whoa, 2.6. 13.6. If I did this correctly, these adds up to 0, right? The 5 deviances. Feel the concept here, right? Feel the concept. We take the next step now. We try to look at each individual, and we come up with a measure of how different are individuals on average. How different from the mean are individuals. If we have a population of large spread, there will be a sort of large difference. If it's just not so much, it's not so much. Anyway, we square them. I don't have the energy to do anything else but this. We add them up. It could be fantastic if someone had this number. Are you there, Jeppe? Or are you busy with other things? Okay. 0.2, which means that the variance of these data is 281.2 divided by 4, n minus 1, which is not quite true. What's that? Okay. And the square root of this becomes 8.38. This is the number that we can understand, actually, the 8.4. 8.4 centimeters. On average, young males are 8.4 centimeters different from the mean height of 179.4. Right? People are not all people are 179.4. We all know that. So just telling that the mean height is 179.4, that's fine, but it's not the full story. I mean, it doesn't tell much of the individual. The variance is a core concept in understanding the population of young heights of males here. Because on average, people are either 8-9 centimeters below, which means when they are on average this below or this much higher, means that more or less plus minus twice this number on each side, right? So people are more or less put themselves 179 centimeters plus minus 16, 17 centimeters. We'll get back to this way of thinking. So it tells a story about the population, an important story, an important concept to us. Finally, there is a... just a few words. I'm not going to... About the n-1n. You can spend a lot of time. And there are some theoretical arguments for this that I can touch on in a few months from now. We're not going to do it in this course. You would need a probability course to fully get to that. However, there is also a kind of intuition in this. The thing is, we should really compare each individual with the true mean. That would be the fair deviance measure, to take each individual and compare him with the true mean of persons. However, we don't have the true mean. We have plugged in the average of the 5 persons themselves here. So the difference to the average where you are part of the sample yourself will typically be smaller than to the true mean, because the x bar will not be the true mean. The x bar will be a bit closer to the data because it's made of the data themselves. So this is just as a point to say, in a way, this measure probably will become a bit too small. It's as a true measure of dispersion of variability, it's a bit too small. And yes, mathematically, it's actually one piece of information too small. And that's why we divide by n-1 instead of n. That's actually not too far from the formal mathematical. Then there are some linear algebra subspaces that boils down to a dimension which is 1 smaller, because we already know, because the sum of the deviances sums to 1, so there is a degree of freedom, a dimension of a subspace that is 1 smaller than otherwise. So that, now I did the math anyway. We don't have to do it more thoroughly than this in this course. That's as much math we're going to do here. I'm not a mathematician. Well, actually I am. But I like much better to be a statistician than a mathematician. So I'm a statistician. One thing more here. Sometimes people combine the standard deviation and the mean to come up with a relative measure of variability. That is, in our case, we would take the standard deviation of 8.4 and divide by the mean height like this and get something like 5% or something like that, right? Roughly. So there is a 5% relative to where we are. There is a 5% standard deviation spread of height among this. Then we could compare with other populations that are put in a completely different scale or something. This is just another. It's called the coefficient of variation, which is combining those two things that I just showed you. These are all nice summary statistics. So this is where, George, we make a small break to